Right, so binary distributions, right? So we have a few problems here. Before we get into that though, I just want to show you this little clip of, in this film, which you may know, Pirates of the Caribbean, there's a scene in one of them where they are playing this game involving die, right? So the idea behind the game is that they want a particular number of die to come up, and they're just basically betting that collectively together, there are a certain number of that particular number. So they're kind of bidding, like, I think there's going to be 4 4s between us when they roll. Or maybe there's 4 5s or whatever they're bidding, right? So this game's called Liar Dice, and it's a game of like you have some knowledge of your own die, and you're trying to think about what other people might have. So obviously people can bluff and things like that, but I think it's an interesting kind of problem to look at when we think about probability, because die are very closely related to this. Yeah? Some of you may have played this before. Yeah. Okay. So that's Liar Dice. And how does it relate to this? Well, we're going to look at a problem like that in a moment for how we can actually calculate these, right? But back to this idea of binomial distributions and looking at the coins, right? That's an easy example. A binomial distribution, let me just kind of tell you those restrictions again. We're looking at like success and failure, okay? So we want to know the probabilities of success and the probability of failure. We usually call those P and Q. Now in your formula that you wrote down, if I think about P, that's just half, right? Because we're looking at tossing a heads, that's our success, right? Now Q, which we can call not rolling a heads, I guess, they wrote that as 1 minus P. And that's obviously because our complementary events in probability, just take away 1 from that, 1 minus the probability of success to determine that. So in this case, that's just going to be half as well, okay? But if you think about the 8 coins and the 5 heads, again, just to explain the intuition there, if you have, for example, your 8 coins here, and I want 5 heads, that's like one arrangement of how this can happen. But what else are you doing with these, right? The idea is that we can arrange these heads between all of these, and these all give me kind of different outcomes, right? So the probability that I'm tossing 5 heads, I have to use our formula. I have 8 coins. I'm choosing 5 of them to be heads, but then I want to incorporate now all of these different chances that these particular outcomes are going to happen. Now, because tossing a coin is a special case, all of these are going to be half, right? But the way you should write this out is still in the typical fashion of, okay, I have half. Now, how many heads do I want? Well, I want 5 of them, so that's half to the power 5, right? And how many tails do I want? Well, I want 3 of them, right? So that would be half to the power 3. And when you think about this, this is going to give you the probability that we are going to toss 5 heads, right? So there's 2 things that's being incorporated here, just to emphasize. It's the arrangements of the coins within that like particular group, but then it's also the probability that we're getting 5 heads. It's the probability that we're getting 3 tails as well. Okay. Any questions about that? No, go ahead and put that in for me. See what you get. Didn't work. What do we get?
7 on 32.
And as a decimal?
0.218.
Okay. So it's about 20% roughly, 21%, 22%, right? So not super high.
The highest odds.
Yeah. So next time we're playing Liar Dice, we can use binomial distributions to work out what's the expected value, right? So again, right, I said that when we're looking at success and failure, it's not just things with 2 outcomes, right? We can sort of manufacture that ourselves. So we've got now 5 dice to roll, find the probability that there are going to be 3 6s. We can apply the same idea. We've got our n value, which is like how many of the particular thing we're looking at. We've got how many of the particular thing I'm looking at. So we usually attribute that to R, so that's 3 6s. Probability of success, well, I know that's 1 over 6. What's my probability of failure? That's just 5 on 6, right? And then we can just put that into our formula. So we've got, we've got 5 coins, and we're choosing 3 of them to be 6s. And it's also my chance of success that I'm looking at. So it's 1 over 6 to the power 3. But then also have to consider, okay, where are my failures? That's going to be 5 on 6 to the power 2. So, I mean, if you want to draw out the die, that's kind of like helpful as well, like just to think visually what's actually going on. Okay, right, so the idea is that we have, all right, these 3 die being arranged within, these can be like whatever, right? But these all have a 1 in 6 chance of happening. That's why it's 1 on 6 cubed. And then these can be, they don't have to be 1s, they can be anything actually. So just leave it blank. It's like a wild card, right? So 5 on 6 square. There's 2 of them.
Remember, 1 is all of them.
1 is, that's true. In live dice, 1 is all of them. Unless you start being 1s though, remember, right? Yeah. All right, cool. Do you want to go this last one yourself? And then I'll put another one up on the board that we can have a look at together. Try this one by yourselves.
Do you want the fraction for that?
Oh yeah, what is it?
It's not really, it really isn't.
Not looking good? Is it, does it actually, is it, what did you say, 120? Yeah.
Over 3,888.
3,800. 3,880. What's that as a decimal?
0.03215021.
So if someone's saying that they have 3 6s and they have 5 dice, it's like a 3% chance that they. Okay, so you got some good odds there. So now you guys know how to play live dice, right? Try the next one yourselves, and then I'll look at a few more.